In this problem solving session 2, we are going to solve problems on two-level atoms and the Heisenberg representation. As the first problem, let us calculate the position and momentum operator x and p in the Heisenberg picture for a one-dimensional harmonic oscillator. And in the second part, find the Heisenberg equation of motion for the operator x and momentum p. So let us do it. But before I do it, let me remind you about the Heisenberg representation. We know that the expectation value of an operator A with respect to a normalized state vector or wave function psi of t, I can write it in this way. So here psi of t is normalized. So this is the expectation value that we calculate using the so-called Schrodinger picture. In the Schrodinger picture or representation, the wave function or the state vector is time dependent. On the other hand, the operator has no time dependency. This I can write because I know how this wave function evolves under this time evolution operator, that is e to the power minus I by h cross. This is the Hamiltonian of the concerned system, and this is your psi of 0 a, and here you have e to the power minus I by h cross h of t psi of 0. This I can write as psi of 0, and I can have here e to the power I by plus I by h cross h of t a e to the power minus I by h cross h of t psi of 0. Now you see, if I define this as my new operator where time dependency is now coming into the operator and the state vector or the wave function is now time independent, right? Now this is the so-called Heisenberg representation of operators. So AH in the operator in the Heisenberg picture is simply e to the power I by h cross. H is the Hamiltonian. Here this h actually stands for Heisenberg. Okay, this is for Heisenberg. And you have here A. This is the Schrodinger operator, which is, or I can simply write it as A. And here I have e to the power minus I by h cross h of t. So with this background or recalling, now we can solve this problem. In this given problem, the system is a one-dimensional harmonic oscillator. So the Hamiltonian for that one-dimensional harmonic oscillator we know is p square by twice m, that's the kinetic energy, plus the potential energy half m omega square x square. M is the mass of the harmonic oscillator and omega is its angular frequency. So this is the harmonic oscillator Hamiltonian, one-dimensional harmonic oscillator Hamiltonian. So we have to find out what is the position operator in the Heisenberg picture. That would be e to the power I by h cross h of t x e to the power minus I by h cross h of t. Now to simplify this expression, we can use the well-known formula, Becker-Hausdorff formula, e to the power lambda a b e to the power minus lambda a. This, you know that this would be b plus lambda commutation between a and b, lambda square by 2 factorial. Let me write it this side here. I have here lambda square by 2 factorial a commutation with the commutator AB plus lambda cube by 3 factorial. We'll have a commutation with AB. Okay, and you'll have higher order terms in the similar fashion. So we have this Heisenberg operator for position would be, then we'll have first term would be x, then here I will have it as lambda is IT by h cross. Okay, I'm just taking the Hamiltonian, just you have to put the Hamiltonian there, and e to the power I by h cross t, let me take it as lambda. So that's what I have here, and this is the Hamiltonian x commutation between h and x. Then the second term would be 1 by 2 factorial, which is simply half IT by s cross, that is your lambda square, and here you will have term like h commutation with hx here, and so on. So let us first of all work out this term and then this term and so on. So if I work out this commutation, hx will get, let me write it, the Hamiltonian is p square by twice m plus half m omega square x square, and here I have x operator. This will give me 1 by 2m p square x. Now because x square commutes with x, so this term, the commutation relation for the other one will give me simply 0. Now this one I can write as 1 by 2m. I can write here it's px plus commutation px p. Okay, and we know that px is equal to minus IH cross, so we'll have here 1 by 2m. From here I will have minus IH cross p. Similarly from the other I will have minus IH cross p. Okay, this is going to give me minus IH cross. So therefore I will have here it as minus IH cross by mp. Okay, now what about the other one? This one also, let me quickly work it out. H of x, this would be equal to Hamiltonian is p square by twice m plus half m omega square x square. Okay, and this already we know, this is minus IH cross by m p. Again here you see this p square and this term will commute, so we have to take the commutation between these terms only. So if I do that, I will have, let me take minus IH cross by m from here this side, and half m omega square also, let me take it out. So I will have here x square p. Okay, and if I do this, you will get it as h cross square omega square x. Okay, I hope it's very simple, or should I do it? Let me do it quickly. So what you will have is minus IH cross by 2 omega square, get cancelled. Again here I have x xp plus combination xp x. Okay, and xp is equal to IH cross, combination of xp is IH cross. So therefore I will have here minus IH cross omega square by 2 IH cross twice IH cross x cap, and therefore I will have simply x cross square omega square x cap. So therefore I have this, if I put all the terms here, xh of t, Heisenberg operator x would be x cap plus 1 by m pt. Okay, I think because it by s cross is there, and h of x is equal to this guy. So therefore you will get the second term as this one, and then you will have terms like 1 by 2 factorial t square omega square x, okay, and then you will have term like, if you do it, you will get omega t cube by 3 factorial 1 by m omega p cap, and if you go further you will get omega t to the power 4 by 4 factorial x cap, and so on. And therefore I can now write x cap, if I take it common, then I have 1 minus omega t square by 2 factorial plus omega t to the power 4 by 4 factorial, and I will get a series like this. And for if I take p by m omega common, then I will get omega t minus omega t cube by 3 factorial plus omega t to the power 5 by 5 factorial, and so on. Okay, I think maybe you will get here a minus sign. So you'll get basically a series, and you can recognize that the first term here, this series is nothing but your cosine series, so you can write it as x cap cos omega t, and the other one you can write it as 1 by m omega p. This one is sine series, sine omega t. Alright, so therefore the Heisenberg representation of the position operator is simply this one. Similarly, exactly following the way I have done it, so you can work out Heisenberg representation for the momentum operator, and you will get it as p cos omega t, please do verify it yourself, minus m omega x cap sine omega t. Right, so this is the Heisenberg representation for the momentum operator. Now let me go to the second part of the problem. Here you are asked to find out the Heisenberg equation for the position operator and the momentum operator. That means you have to just work out dx's of dt, and you know the Heisenberg equation of motion, that would be 1 by I h cross x h, and the Hamiltonian here. Now this Hamiltonian is in the Schrodinger picture actually, and therefore let me write x is the expression that just now we got, that would be 1 by I h cross here, and here xh, this one we worked it as x cos omega t. There are other ways also to do this, but let me do it this way. I have here p by m omega sine omega t, okay, and this commutes with a commutation we have to work out with this one. Hamiltonian is p square by twice m half m omega square x square. Okay, we have to just work out this commutation relation. So this is going to lead us to, let us do it. You will get, so I have first term, if I take, let me take cos omega t out, and here I have x and p square by twice m. I just have to take the cross term because I know x and x here, this term commutes, and p commutes, so I have to deal with the cross term only. And the other term that I have to deal with is 1 by I h cross here, 1 by m omega sine omega t, okay, and you will have here p half, okay, I could have taken that also out, but anyway, m omega square x square. So anyway, if you do the mathematics, very straightforward, you can do it. You will finally get it as 1 by m. Please do the steps yourself. You will get it as p cos omega t minus m omega x cap sine omega t. This is what you are going to get. So by the way, this is not, let me put it in this way, bracket. So this is what, and what this guy is, this already we know, that is nothing but the momentum operator in the Heisenberg picture. So therefore you have 1 by m ph. So this is the Heisenberg equation of motion for position operator. And similarly you can show that dph of dt, Heisenberg equation for the momentum operator would be minus m omega square x h of t. Let us now work out this problem. The Hamiltonian due to the interaction of a particle of mass m, charge q and speed s with a magnetic field pointing along the z-axis is h is equal to minus qb by mc to sz. Sz is the z component of the spin vector s. Write the Heisenberg equation of motion for the time dependent spin operators sx, sy and sz. Let us do it. Before we do this problem, let me remind you some facts about the spin operator s. And we know that we can write this spin operator or the spin vector s as in terms of the Pauli vector sigma, s cross by 2 into sigma. Sigma is the Pauli vector, and component wise we have sx is equal to x component of the spin vector would be equal to h cross by 2 sigma x. Sigma x is the Pauli matrix, x component of the Pauli matrix, and you may recall that sigma x is equal to 0 1 1 0. Similarly we have sy is equal to h cross by 2 sigma y, and sigma y is equal to 0 minus I 0, and sz is equal to s cross by 2 sigma z, and sigma z is equal to 1 0 0 minus 1. Also, you know the commutation relation between these matrices, say sigma x sigma y, you will get 2i sigma z, sigma y sigma z will give you 2i sigma x, and we'll have say sigma z sigma x will get 2i sigma y. Right, so using this you can immediately see that the commutation between sx and sy will give me I h cross sc. Commutation between sy and sz is going to give us I s cross sx. So you can notice the cyclic order here, and we have sz sx is equal to I s cross sy. Let me now come back to the problem, because we are asked to find out time dependent of this operator sx of t. That means we basically what is asked is the Heisenberg representation of the spin component of the vector sx. Similarly for the other components, so this would be equal to e to the power I by h cross h of t sx e to the power minus I by h cross h of t. Here this Hamiltonian is given as minus qb by mc sz. Okay, what I can do, I can write e to the power I by h cross h of t is equal to e to the power minus I by h cross qb by mc sz. For simplicity purposes, let me write it as e to the power lambda sz, where I am taking my lambda is equal to minus I by s cross qb by mc into t. Okay, so therefore exactly like the previous problem, I can have Sx of t is equal to e to the power lambda sz Sx e to the power minus lambda Sz. Now applying the formula that we utilized in the previous problem, Becker-Hausdorff formula, we have Sx plus lambda commutation between Sx and I think it would be Sz, rather Sz Sx. Then we'll have lambda square by 2 factorial Sz commutation of Sz and Sx and so on. If we do it, you will get Sx plus Szx commutation will give me is cross lambda Sy. Okay, and here you will get it as minus is cross lambda square by 2 factorial. You will get it as Sx and so on. In fact, in this, it's very easy to show that I can write, if I take lambda dash is equal to is cross lambda, then I can write Sx of t is equal to Sx. If I take it common, then I have 1 minus lambda dash square by 2 factorial plus lambda dash to the power 4 by 4 factorial, and we'll have Sy would be lambda dash minus lambda dash cube by 3 factorial plus lambda dash to the power 5 by 5 factorial and so on. So this series is now well known to you. This would be, this one is your cos lambda dash and the other one would be sin lambda dash. But lambda dash is equal to is cross lambda, which is is cross lambda is equal to we wrote it as minus I by s cross qb t by mc. So this is going to give me qb by mc, okay, into t. All right, so but if I define my frequency omega as minus qb by mc, if I define it as angular frequency omega, then we can write Sx of t is equal to Sx cos omega t plus Sy. Okay, I think okay, you will have Sy sin omega t. So this is what we are going to have. Hopefully I'm doing it correctly. Please verify it yourself. There should not be any missing. Okay, let me take it plus, then this is cos lambda. I will get it like this. Okay, I think, yes, I think it is correct. No, as per, okay, let me define it as minus, better, then I will have it as minus. Okay, this is what I'm going to have. Now what about the equation of motion? So dsx of dt would be equal to The first term is going to give us Sx omega sine omega t with minus sign, and here I will get Sy omega cos omega t. Therefore, I have minus omega Sx sine omega t plus Sy cos omega t, and it will turn out that we can actually verify it later on. We can similarly work out what is Sy. You will find out that this is nothing but your Sy. So this is what we are going to get. Of course, you have to get this, you have to similarly work out Sy, then only you can see that this is nothing but Sy. But let me show you another method which may be more straightforward to work it out. We know the Heisenberg equation of motion for this operator. So we have 1 by I s cross Sx of t, the commutation between the operator and the Hamiltonian. I have here 1 by I s cross. This Sx of t I can write it as e to the power I by s cross h of t, Sx of 0 e to the power minus I by s cross h of t, and this Hamiltonian. Now, because this Hamiltonian commutes with this evolution operator, or either way, it will be minus I by s cross h of t h. It's very easy to see that this commutes, and because of that, I can write dxx of dt is equal to 1 by I h cross. Just look at this expression here. I can write it as e to the power I by h cross h of t, Sx of 0. This is the Schrodinger representative operator of spin component of x component of the spin operator, and here I have the Hamiltonian as minus qb by mc. It is sz of 0, okay, e to the power minus I by s cross h of t. This I can write. Now I have 1 by I by s cross. Let me take this out. So I have minus qb by mc e to the power I by h cross h of t, sx of 0, sz of 0, e to the power minus I by s cross h of t. Now commutation between sx and sz is minus I s cross sy, right? So therefore I will have okay, let me write it properly. I have 1 by I s cross qb by mc I s cross, and I will have here e to the power I by s cross h of t, sy of 0, e to the power minus I by s cross h of t. And what this is nothing but the Heisenberg representation of the spin operator, y component of the spin operator, sy of t. So I have here qb by mc sy of t. Now if I define my frequency omega as minus QB by MC, I will get it as minus omega Sy of t. So this is what I have. dsx of dt is equal to this. So I think this is more straightforward. Let me see what we got earlier. Yes, this is what we got. Okay. Similarly, please show we can obtain the Heisenberg equation of motion for y component of the spin operator, and if you do it, you should get it as omega sx of t. On the other hand, if you take for z component of the spin operator, it will be 0, so it is not going to evolve in time. Let us now work out this simple problem. A two-level atom has a Hamiltonian H, so it is given in terms of a 2 by 2 matrix with the component H11, H12, H21 and H22. Find the appropriate expansion coefficients to write this completely in terms of the 3 Pauli spin matrices plus the unit matrix. Let us do it. So we can write this Hamiltonian H11, H12, H21, H22 in terms of the Pauli matrices sigma x, sigma y, sigma z, and the identity matrix. It would be 2 by 2 matrix here. So coefficients are say A, B, C, and D. So this is what we have. Now if I know what is sigma x, sigma y, sigma z, and sigma I, so let me write it. The first term would be sigma x is 0, 1, 1, 0. So I'll have 0, A, 0. Sigma y, I know 0 minus I 0. So here I have 0. I will have minus IB 0. And the third term would be C 0, 0 minus C. And the last term would be, because sigma is identity matrix, so here I'll have D 0, 0, D. So if I add all of them, then I will get C plus D, A minus IB, A plus IB, and I will get minus C plus D. So now if I compare it term by term, then you will have H11 would be equal to C plus D, H22 would be equal to minus C plus D, H12 would be equal to A minus IB, and H21 would be equal to A plus IB. And from these two terms, immediately you see that I will get D is equal to H11 plus H22 divided by 2. I just have to add these two terms and then you will immediately get it. Similarly, you will get C is equal to, if you subtract them, you will get H11 minus H22 divided by 2. Again, from here you will get A is equal to, if you sum them up, you will get H12 plus H21 divided by 2, and B you will get it as H21 minus H12 by 2I, or I can also write it as minus I by 2. If I take it up there, or if I take plus inside, I will have H12 minus H21. So this is what I will get. Now if I put everything, So I will get h is equal to half of, if I take half out, then I'll get h12 plus h21 sigma x plus I h12 minus h21 sigma y, and I will have h11 minus h22 sigma z and h11 plus h22 sigma I. That's the identity matrix, or if you're not comfortable with sigma, you can simply write identity matrix I. Okay, so this is the solution. Let us now work out this problem. You have to prove this relation. In fact, this relation we have obtained and we discussed in the context of dress state in lecture 5, and I asked you to show it, but here let me do it and explain the things little bit more clearly compared to the lecture. In the lecture, if you recall, we got this relation tan theta. Theta is the Stackelberg angle. Tan theta is equal to omega, that is the Rabi frequency, divided by the omega tilde minus delta. Omega tilde is the generalized Rabi frequency, which is equal to square root of omega square plus delta square. Delta is the detuning parameter. Then I asked you to use this trigonometric relation to prove this relation here, and tan 2 theta is equal to 2 tan theta divided by 1 minus tan square theta. Let me first work out what is 1 minus tan square theta. 1 minus tan square theta is equal to 1 minus tan theta is omega divided by omega tilde minus delta whole square. Let me simplify it. I will have in the denominator omega tilde minus delta whole square. Here I will have omega tilde minus delta whole square. If I open it up, I will get omega tilde square plus delta square minus twice omega tilde delta minus omega square. And I know that omega tilde square is omega square plus delta square. Okay, then I have here delta square minus twice omega tilde delta minus omega square divided by omega tilde minus delta whole square. So from here I get 2 delta square minus twice delta omega tilde divided by omega tilde minus delta whole square, and if I take 2 delta common, I will get delta minus omega tilde divided by omega tilde minus delta whole square. And from here you see that I will get, because this is square, I will get 2 delta divided by delta minus omega tilde. Okay, so this is my 1 minus tan square theta. Now let me work out what is tan 2 theta. Tan 2 theta is equal to 2 tan theta, and tan theta is omega divided by omega tilde minus delta, and 1 minus tan square theta already we worked out, and that is 2 delta divided by delta minus omega tilde, which I can write as twice omega divided by omega tilde minus delta, and here I will have delta minus omega tilde divided by 2 delta. So this will lead me to minus omega by delta. So I have proved it, but let me make the this limit of the angle, that this theta has to lie between 0 and pi by 2. Let me explain it little bit. 1 minute. So I will have it as this. Let me explain this limit. What about this limit? Okay, First of all, recall that in terms of the Stuckelberg angle, I can write my dress state Kt plus as sine theta Kz plus cos theta Kt and minus Kt as these plus Kt plus and plus Kt and minus Kt are the dress states, and here I will have here cos theta Kz minus sine theta Kt, and also we have tan 2 theta, already we know that is omega tilde omega by delta, or tan theta is equal to, we have it as omega by omega tilde by delta. Either of this expression is going to be useful when I'm analyzing it. Let me consider one case where this detuning parameter is much smaller than say minus omega. Omega is the Rabi frequency, and we assume that the Rabi frequency is positive, say omega is greater than 0 by convention. Then let us see what we'll get. We'll get, what about the angle if this is the case? Okay, if delta detuning parameter is much less than minus of omega. Now tan theta is equal to, already I wrote, omega divided by omega tilde minus delta, and because omega tilde is equal to omega square plus delta square, so because I have your delta is much smaller than omega, so I therefore can write that omega tilde is nearly equal to omega. So I have here omega divided by omega minus delta, which I can actually write as 1 divided by 1 minus or plus minus delta by omega. Now from here you can see that I have minus delta by omega is much greater than 1. So therefore, because of the fact as delta minus delta by omega is much greater than 1, so I can consider that tan theta is approaching 0. That means that angle theta is nearly equal to 0. So this is one of the limit of the angle that we have, that it is one bound. And another one, let me consider the other extreme. In the second case, let us say I have this detuning parameter is much larger than the Rabi frequency. So this actually imply that omega divided by delta is much less than 1. Okay, we'll see what it leads us to. Tan theta is equal to, now I have omega. Okay, now let me write omega tilde minus delta. So omega tilde is equal to omega square plus delta square, and because of this I can write omega tilde would be nearly equal to delta, right? Because it's much smaller than omega. Rabi frequency is much smaller than the detuning parameter. So I have here omega divided by delta minus delta, so it tends to infinity, it means. So this implies that my theta approaches the angle pi by 2. So hence we have the angle is lying between 0 and pi by 2. So this is the meaning of these bounds.